Good afternoon, everyone. My name is Yingheng Wang from Department of Computer Science at Cornell University. I'm an incoming PhD student there, and if you see this pre-recorded video, that means I cannot make my way to the conference center. But I'm still super happy to represent our team to show our solution for this task, which is predicting PTHrP result. And this is a joint work contributed by me and Dr. Wei-Shen Pan, who is from Department of Population Health Sciences at Weill Cornell Medicine. And also, there are two other collaborators, who are Dr. Serena Yan and Dr. Fei Wang from Department of Pathology and Laboratory Medicine, and also Department of Population Health Sciences at Weill Cornell Medicine. So, first of all, I will briefly summarize the task and our pipeline. So Dr. Spice maybe has introduced some background of this task. So basically, for one sentence summary, it is aiming to predict PTHrP results by using patients' other laboratory test results at this time order. So for the pipeline, we first did several steps to understand data and construct the input feature space, which are data preprocessing, feature extraction, and feature selection, and imputation. Then we did some empirical studies to select the best model and set of hyperparameters. Our experiments are evaluated through five-fold cross-validation, which helps to prevent overfitting. Here, I will briefly go through some details and necessary information for you to understand the dataset better. So the dataset has been split into a training set and a testing set. For the training set, there will be 1,064 samples, and for the testing set, there will be 266 samples. Those data are collected from a decade between 2012 and 2022. So here I listed the definition of each column of the input data. Some of these columns are important for our future prediction. They are the value of the lab tests, the lower and upper limits of the normal range, and the days of the lab test. So another thing is that it should be noted for patients having multiple PTHrP orders, this dataset retains only the first order with its associated data. Next, I'm going to introduce something regarding the label. From the box figure, you may have an overview of the distribution of the PTHrP values, so most of the data will be located in a very small normal range, which is from 0 to 3. On the contrary, a relatively small number of abnormal data will be scattered in a very large range. Therefore, we can intuitively conclude that this task is very difficult to be defined as a regression task. Actually, our empirical study shows that the results will be very poor if we do regression on this dataset. So in our final solutions, we model this task as a classification task simply using the binary value of the normalcy, which is shown in this right table. And here we will introduce some information about the test classes of the dataset. So this dataset contains a large number of test classes, which is about 3,000. However, most of those tests are only measured in a very small number of patients. The statistics are shown in this figure. The x-axis is the number of assays, and the y-axis is the proportion of patients who have at least one measurement. So you can find that there are about 2,700 assays being measured under 10% of patients, and only 65 assays are measured in at least half of the patients. So in our experiments, we only use these assays to construct our input feature space. Besides, similar to the PTHrP result values, for another given assay, the normal range may be different in each measurement due to different hospitals or devices, such that we will do some normalizations before we start the training. Here are two other important columns of each lab test order, which are the medical service and encounter type. From these two tables, you may notice that the abnormal proportion of each column differs a lot. Therefore, we need to encode such useful information into our input feature space. Since there is only a small number of data samples that don't fall into these categories, we simply put the other categories together. So here we apply one-hot encoding for these two features. As an example, for medical service, we encode general medicine as a vector of 1, 0, laboratory as a vector of 0, 1, and others as 0, 0. Although we have decided the number of assets that will be used for constructing input feature space, we still need to decide the length of the observation window since lab test results from a long time ago may be meaningless for prediction. So here, we designed two strategies for our feature extraction process. The first is setting the observation window as some certain time measurement units, for example, a month, a season, or a year. The second strategy is to set a fixed length of the observation window first, and then for those lab tests which don't have measurements in such a time window, we will look back until there is a measurement for these lab tests. For this part, we find the first strategy is much better in prediction performance, and I will introduce some of our experimental results afterward about how we finally determine the length of the observation window. We also conduct some normalizations here to unify the different normal range of different measurements. The formulation is quite simple. We use the lab test result value minus the lower limit of normal range over the upper limit of normal range minus the lower limit of normal range. And below, I provided an example to better illustrate it. You probably will think of using the binary value of normalcy to replace the real values. We also tried this strategy but failed on the model performance, so finally we just discarded these strategies in our final solution. We also calculated some statistics of the selected lab tests in the observation window and used them as features. Some basic ones are the minimal, the maximal, the average, and the latest value of the observation window. And besides, we also regress the lab test values with the time and calculate the scope of the line as a feature. And we also tried the number of measurements and the binary indicator of whether there is no data observed in the observation window, but the performance decreased on the public leaderboard, so we finally discarded them. Here we can conclude the original input feature size calculated by the number of assets times the number of those statistics plus 4, which is the one-hot encodings of medical service and encounter type. Then I will introduce how we do feature selection and imputation. We tried some statistical testing methods to select significantly meaningful features, but we found that directly using entire input features would be much better, so we don't apply this step in our final version. And for imputation, we resort to k-nearest neighbor imputation approach, which imputes each sample's missing values using the mean value from k-nearest neighbors. The idea is two samples are close if the features that neither is missing are close. And the imputation process will benefit the final performance a lot, and I will show you some results afterward. Here are 3 steps of our model training. The first step is to pre-train an XGBoost model with all input features. And I provided an illustration of XGBoost model on the right side. I'm not able to dive into the details of XGBoost, but you can simply think of it's an ensemble model of many decision trees. So if you are familiar with pre-training technique in deep learning, the pre-training term I mentioned here is totally different. Here we are just doing supervised learning to learn an important score for each feature. Then we can order the features by their scores and filter some unimportant ones. The importance type is a hyperparameter, so you can just try different values to see which one is the best. Basically, gain indicates the improvement on classification accuracy by using a feature to do tree splitting, and cover indicates the relative quantity of training samples concerned by a feature, and weight just tell you how many times the model uses this feature to do tree splitting. After experiments, we find gain is better than others on this dataset, so we just use the selected features to retrain a model and do prediction by the gain as a feature importance type. And this combination uses F1 score as the evaluation metric, so we also tune the hyperparameters based on this. For preventing overfitting, we apply 5-fold cross-validation to evaluate the model's performance. Here are some critical hyperparameters listed, which are the length of the observation window, the usage of normalcy, the usage of normalization, whether we keep the outliers, the method of feature imputation, and the number of selected features, and also the prediction threshold. So on this slide, I just marked the optimal parameters in red color. So we use the last whole year as the observation window, and we keep the original value for the normalcy, and we do some normalization after we using the original values. And also for outliers, we just keep it. We didn't do some operations like replace all the outlier values by the missing or the mean or median values. And also we try the KNN imputation methods to impute missing values in the features. And for the last step, we will set the number of selected features at 200 and set the prediction threshold as 82%. And here are some other implementation details. So finally, we just choose the single XGBoost model, which is a tree-based model, as our final machine learning models. And we will provide how we decide this model as our final model. And there are three critical hyperparameters for XGBoost, which are the number of the trees, the max depth of the trees, and the learning rate. And here we also use a strategy, which is a model vaulting to prevent overfitting problem. The idea is quite simple. So the model with more trees, larger depths, and lower learning rate may have a strong fitting power, but weak generalizability. On the contrary, a model with less trees, smaller depths, and larger learning rates can generalize well, but not fit the training set well. So we ensemble three models with different hyperparameters to balance the fitting power and generalizability. And here, I will use several slides to briefly introduce some strategies we tried but discarded finally. During our experiments, we found the ordering of input features will highly influence the model's performance, so we come up with another approach to calculate the importance scores of features, which is the permutation importance. The idea is the model's performance will fluctuate when we randomly shuffle a certain feature. So the variation of the model's performance indicates how much the model depends on this feature. This approach can also solve two limitations in the impurity-based feature importance used in XGBoost. One is impurity-based importance is biased towards high cardinality features, which means a feature with more unique values will be more important. But in permutation importance, it will treat each feature equally. And another is impurity-based importance is computed on the training set, so it can reflect the generalizability of those selected features. However, the permutation importance will be computed on the validation set, which can guarantee the generalizability. But this method also has a limitation, which is when features are collinear, permutating one feature will have little effect on the model performance because it can get the same information from a correlated feature. So we have to apply hierarchical clustering first to filter some collinear features, which may result in information loss. Actually, we tried this approach, but it cannot perform well, so we didn't use it in our final version. Another one is model cascading. We train a new model using borderline samples in validation sets and cascade this model right after our main model. So this is kind of a whole pipeline. So we use this pipeline and evaluate on the testing set, but the performance is not good. So we think the problem is the overfitting. And next, we try two kinds of similarity-based hard sample augmentation. So the first version is quite simple. Since the borderline samples in validation sets are too less, we choose some similar samples in the training set to extend the hard sample set. And we also tried many distance metrics here. However, this method still cannot do well due to maybe overfitting problem. And the second version of the similarity-based hard sample augmentation is only to keep the majority of the similar samples in the same label. So this visualization shows after augmentation, the space may become more dividable, but the performance on the public leaderboard is not that good. So maybe the problem is the overfitting, but there is another reason, which is that the training set and the testing set may have different data distribution, so that if we fit the training set very well, it cannot generalize to the testing set very well. So that I think that may be the problem. So next a few slides, I will provide some experimental results and interesting findings in our empirical studies. So for XGBoost, the model achieved the best performance using a year as the observation windows and the concatenation of all of the statistics of the features. Now our experiments are evaluated through 5-fold cross-validation, which is illustrated in the right figure. The idea is that we split the training set into 5 folds, then train the model on 4 of them and validate it on the remaining one. And we will repeat this process for 5 times and output an average performance for the evaluation. However, on this slide, you can notice that when we compare two models which are XGBoost and neural networks, for neural networks, it would be better to use half a year as the observation window. I guess the reason is that different models learn different patterns across features and samples.